everyone. Uh, Good evening, everyone. So, we, Dr. 𝗕𝗫𝗄𝗎 and myself, Dr. Susri Ipshita, welcome you to the fifth day of FSFM 2025. So, for today's session, this is our ninth session. For today's session, we have Dr. 𝗕𝗵𝘂𝗃 𝗠𝗃. Now, Dr. 𝗕𝗃 is currently working as an associate professor in the School of Mechanical Engineering of KIT deemed to be University Bhubaneswar. He has published more than 40 papers in highly reputed international journals. His major areas of interest include decision modeling, supply chain management, sustainability, data analytics, operations, and quality management. He has been honored with the Outstanding Research Paper Award from the Institute of Engineers in 2020, 2024, and 2025. He is also impaneled as a lean consultant under the MSME competitive scheme, where he assists smaller enterprises in optimizing their processes and improving global competitiveness through lean methodologies. Thank you, sir, for joining us today. So the screen is yours.
Yeah, thank you, ma'am, right, for your kind introduction. Am I audible, ma'am, clearly?
Yes, sir.
Yeah,
Yes,
yeah.
sir.
So once again, right, I would like to thank the ma'am, right, for kindly introducing me. Uh, I am right. So very good evening to everyone present here. So myself, Dr. 𝗕𝗵𝘂𝗃 𝗠𝗃, right, from KIT University. So it is my pleasure, right, to be the part of this ATAL FDP. And today I will be talking about decision analytics in semiconductor industries. What type of the decisions are made in the semiconductor industry? So let me just share my PPT.
Sure, sir.
So is my PPT visible to everyone?
Yes, sir.
Okay, ma'am. Thank you. So my topic, right, for today's session is decision analytics in semiconductor industry, right? So we have to understand, right, what type of the decisions are made in the semiconductor industries, okay? And how the companies are, right, resolving those decisions or taking those decisions. So, right, whatever, right, the examples that I will be presenting here. So all the examples will be right from the published literature available online, right? So from there I have picked, right, few examples, right, where the companies are making the decisions in the semiconductor industries. There are so many lots of examples are there, but I have selected a few. So first, the example is, since it is a part of the published paper, so I will just tell the reference, right, for the further reading if someone interested to go in the details with respect to the semiconductor industries or with respect to that particular paper, you can go through that. So the first paper is a novel approach based on gray simplified west-worst method and gray possibility degree for evaluating materials in semiconductor industries. So this is a reference, right? This is a paper published in 2023 and it is published in Soft Computing Journal, is one of the top rated journal. So what they have done, right? So the objective of this paper is to choose an appropriate alternate supplier, right? Based on, right, certain conflicting criterias are there. Let the company has to decide. So there are a plethora of underfill suppliers and selecting the most suitable underfill for preparing a flip chip package is critical as there are conflicting criterias like glass transition temperature, coefficient of thermal expansion, elastic modulus, coefficient of moisture expansion, fracture toughness, shear strength, and flowability. So if you have to select a supplier for the underfill, right, material, then how to select? So this type of the decisions is to be made right now. How to do that? So what they have done. So whatever, right, we are going to discuss here, we will just discuss, right, what is the objective, what the decisions the company is making or the author is trying to address, and what methodology they have adopted, right? We will not discuss how they have adopted because we cannot discuss each and every paper in detail, right? So you have to go through that. So at the last, after giving certain examples, right, I will be taking few techniques which are used for making the decisions. So I think this problem is clear to everyone, right? So a supplier is to be selected, right, for flip chip package material or for the underfill, right, material, right, for preparing a flip chip package, right? And there are conflicting criterias, right? No one supplier is right exceeding in all the criterias. Like we have to select a car, right? If we have to select a car, that car, right, cannot stand in all the criterias, right? So what they have done, right? They have employed the combination of gray simplified west-west method. This is also one technique, and the gray possibility degree analysis waste method to select the most suitable underfill material for reliable flip chip packages as a real world problem. So they have utilized these two methodologies for solving this problem related to the semiconductor industry. Now take example 2. So in example 2, another paper, right? The title is Evaluating the Supplier Sustainable Development of the Semiconductor Industry using VWM and fuzzy topses. So this is again a paper published in one of the SCI journal. So, right, the objective here is to identify the key sustainability indicator in semiconductor industry and rank them according to their relative importance. So if you have to measure the sustainability in the semiconductor industry, so there may be certain factors. So first we have to identify what are the key sustainability factors and how to rank them, right? Which is the most important factor which is indicating the sustainability of that particular organization. So what they have done a review of large volume of literatures. They have taken the expert interviews and they have determined 4 dimensions, right? I think everyone knows with respect to the sustainability. 3 dimensions are there, right? So environmental, social, and economic. And fourth one they have taken is innovation. And they found the 13 criteria, right, to develop an evaluation framework. Now, what they have done, they have obtained the weights of the evaluation criteria using VWM method. So they have used the VWM method, West-West method, for calculating the weights of the criteria, right? So there are certain criteria. Based on those criteria, certain either the supplier is to be ranked or supplier to be rated or some other alternative is to be rated, right? So that we are talking here. A reliable method for determining the weights in MCDM problem, right? And lastly, the TOPSIS is used to prioritize the indicators, right? And right, some of you may not be right aware of this terminology. So when we will take the examples at the end, when we will take the specific technique, I think every term will be clear to each and everyone. So I'm just giving the examples, right? What type of the decisions are made in the semiconductor industries, right? So those decisions may be with respect to any material, sustainability, right? Capacity allocation, and with respect to any other thing. Next paper is a multi-criteria decision-making approach for capacity allocation problem in semiconductor fabrication, right? So this is they have solved the capacity allocation problem, right? And this paper is again published in very reputed journal, International Journal of Production Research. Okay, so what they have done, so first the objective is to evaluate and select the capacity allocation plan in semiconductor fabrications. So the allocation of capacity for manufacturing different types of products is important for the competitiveness and the future development of the enterprise. So a particular plant, particular organization is making right various types of the product. Now how to allocate the capacity, right, as per the requirement, right? It is very essential and this problem is to be solved. So what they have done, they have used a combination of methodology. They have used the fuzzy analytic network process. They have used the fuzzy Delphi method, constant programming, and they have done benefit, opportunity, and cost risk analysis. And this they have provided this comprehensive framework to solve this problem. Now, how they have done again is we have to go through that paper, right? We have to learn more about that. So next, right, the problems or that decisions that are made in the semiconductor industry, maybe with respect to, right, so this is another paper, barriers to manufacturing integrated circuit chips in the Indian semiconductor manufacturing industry using gray influence analysis. Right, so this is a reference, those who would like to go through that. So recently published in the year 2025, and this is a business process management journal again from the Emerald. So the objective of this paper is to identify and rank the barriers to manufacturing integrated chips in Indian semiconductor manufacturing industry. Right, so you know that India's ongoing efforts in developing the semiconductor, right, are going on, but they are not so, we are not leading in that manufacturing, right, in the area of semiconductor. So what are the barriers, right, that the India is facing or the industries in India are facing with respect to the manufacturing the ICs or semiconductor chips? So what they have done to solve this problem, right, they have developed, they have used, right, gray influence analysis, right, and they have ranked them. They have also developed the causal relationship between the different barriers. So this again, right, something more that if you have to develop how these factors are interacting, how these barriers are interacting, then apart from the ranking, they have also developed, right, one causal relationship. Another decisions, right, maybe with respect to the, right, compare the suitabilities of several locations for building localized wafer fabrication, right? If you have to take the decision with respect to the location, where we should locate our facility for manufacturing the wafer, right, required for semiconductor chip, right? Then how to solve this problem? So they have again applied two MCDM methods. So MCDM stands for multi-criteria decision making, right? So we have, right, various criterias, and based on the various criterias, we have to select one particular suitable alternative. Right, so they have used this AHP and the TOPSIS. These are two, right, techniques, right, they have used to find the suitable location, right, for setting up the facility for wafer manufacturing. Then next, right, maybe, right, next paper is there, which is utilizing FDM and ANP to construct a sustainability balanced scorecard for the semiconductor industry, right? So we already know that balanced scorecard is all about understanding the performance of a company, how the company is doing, right, on the financial side, on the customer side, on the internally performance, right, how, what is happening. Okay, so they also added, right, one more parameter for that to understand with respect to the sustainability, right? So what they have done, so again, this is also published in the old paper in 2011, but again, it's a very good general expert system with applications. So the objective is to propose a sustainability balanced scorecard framework to measure the sustainable performance for the semiconductor. So what they have done, so they have identified the 25 measures they have taken for sustainable performance. So through expert questionnaires they found, and they have used the fuzzy Delphi method, right, to identify those 25 measures. Further, the relative weights of the selected measures were determined using analytic network process. So they have used again the ANP methodology, right, to rank them. So fuzzy Delphi method was used to identify the few important one, right? So they may have selected, right, like 50. So out of the 50, right, they right finalized 25 based on the fuzzy Delphi method. Again, that is with the help of the expert input. Okay. And again, they have applied this fuzzy analytic network process to rank them, to determine their weights. So another, right, decision that can be made is to understand, right, the impact of environmental and social sustainabilities with respect to the general firm operational efficiency. So each and every company is giving focus on environmental side, on the social side. So how it is impacting the operational efficiency of the firm, if you have to understand that. Okay, so to solve that problem, what the authors have done or proposed, they have employed a sample of 129 listed Chinese semiconductor companies, and they have used slack based data envelopment analysis methodology to reach to the, to understand how the firm's operational efficiency is impacted. Then next, decisions, right, that company is making or that can be done, right? So this is again a paper published in, right, another very reputed paper journal, Computers and Industrial Engineering in 2023. So they are, right, utilizing the Bayesian decision analysis for optimizing inline metrology and defect inspection strategy for sustainable semiconductor manufacturing. And they have also proposed an empirical study, right? So what they are doing, they are, right, proposing a one decision framework for dynamically optimizing the defect inspection strategy and inline metrology resource allocation, including the sampling rate, the sampling period determination, and selecting the specific defect inspection lots to enhance the information gain and coverage in high mix wafer foundry. So I think some of you may be aware of this. Bayesian decision analysis is a probabilistic analysis done, right, to understand, right, posterior probabilities, right? So they have used this for optimizing inline metrology and defect inspection for semiconductor manufacturing. Then we have another, right, article or another problem that is solved, right, that another decision is made in the semiconductor industry. So they have, the title of this paper is an explainable fuzzy collaborative intelligence approach for prioritizing possible measures to tackle challenge in the semiconductor manufacturing supply chain localization, right? So there are various challenges, right, in setting up the semiconductor manufacturing facility locally. So what are the challenges, right? And what are the possible measures, right? And which measure is most effective in tackling those challenges, right? So they have solved this problem, or they have made the decision with respect to the semiconductor manufacturing supply chain localization. So again, this article is published in Operational Research, and I think this is recently published, or it is to be listed in 2026. So the objective here is to identify key challenges in semiconductor manufacturing supply chain localization and prioritize feasible mitigation measures using an explainable fuzzy collaborative intelligence framework. So first they have identified key challenges, right? Then they are identifying the measures, means solutions to tackle those challenges, right? So to solve this problem, again, they are using the multi-criteria decision-making, right, approach. They are using that. And what they are doing, they are identifying the weights of the challenges, and after that, they are comparing each solution against this challenge, and finally, they are doing fuzzy collaborative, right, summation, right, or integration to come up with the final ranking. Then the last, right, example that again I have taken is with respect to the material itself. So this is a paper again published in Mathematical Problems in Engineering, right, in 2022 by Wiley. So what they have done, the selection of semiconductor packaging material by combined fuzzy ASP entropy and the proximity index value method. So they have used the two methods. So there are n number of, right, multi-criteria decision making approaches, MCDM, are there. So there is a, right, the application area of each and every, right, MCDM is different, or the advantage and disadvantages are always present with respect to each and every MCDM method. So the objective here is selection of semiconductor packaging material. So what they have done, so in this study, right, 31 carboxylic acids were ranked based on the 6 different criterias: melting point, molecular weight, boiling point, acid dissociation constant, solubility, and the number of carboxylic acid functional groups using combined fuzzy ASP entropy and the proximity index value. So what they have done, we have certain criteria, and they have identified the weight of the criteria using the fuzzy ASP entropy methodology, and they have ranked the alternate materials by using the proximity index value method. So again, this is how, if you have to identify a particular material, right, then there are certain conflicting criteria, then again how to do that. So again, for that we can also rely on certain methodologies, right? So those methodologies are mentioned here. So these are the, right, certain decisions that we make in the semiconductor industry. So the decisions, right, maybe with respect to the selecting the suppliers, right? It may be with respect to the calculation of sustainability indicators. It may be with respect to the capacity allocation problem, or it may be right with respect to the understanding the barriers of manufacturing in manufacturing of ICs in India. It may be with respect to the local location for semiconductor factory, or it may be with respect to the sustainability balanced scorecard, or the decision may be with respect to assessing the performance of a company, right? Or it may be with respect to optimization of inline metrology and defect inspection strategy, or it may be again with respect to the understanding the challenges in semiconductor manufacturing supply chain localization, or it may be with respect to again the packaging materials. So there are n number of examples. So I've just picked right few right that came to my mind, right, or that I thought of worth mentioning here. So now let's see, right, the methodologies, right, or the methods that can be utilized for making such decisions. So one of the method that I will be explaining right to everyone is the TOPSIS method, right? So it is again a very popular and MCDM method utilized for wide variety of application. You can understand the importance. I will show you right some of the slides. So what is the TOPSIS, right? So this TOPSIS stands for Technique of Order Preference Y similarity to ideal solution, right? So this is a talk technique for order of preference Y similarity to ideal solution. It was proposed by Huang and Yoon in 1981. It is the most popular technique for making the decisions in the any of the industry. It may be the semiconductor industry, or it may be right any other area also. So it is not like that whatever the techniques that I have explained, whether it is the MCDM approaches, whether they are the data analytics approaches, techniques, or again the AI machine learning right approaches, they can be utilized in any of the industry. But I quoted some of the examples right with respect to the semiconductor industry because of based on the theme of your Atal FDP. So this method is based on the concept that the chosen alternative should have the shortest distance to the positive ideal solution and the farthest distance to the negative ideal solution, right? So you will not be able to understand at this point of the time. I will tell you. So the concept is that we will be choosing the alternative which is right farthest to the negative one and which is shortest to the positive one. Now, what is the positive ideal solution and what is the negative ideal solution? We will see. So the application of the TOPSIS is very broad, right? It can be used in any of the industry, right? In the varieties of decision making, right? Maybe with respect to the supplier selections, it may be with respect to the plant or the warehouse location selections. It may be with respect to third-party logistics service provider selection. It may also be used in forecasting. Some of the papers are also present which are utilizing the TOPSIS methodology for forecasting also. There are varieties of applications are there for TOPSIS. So you can see, right, the importance of this TOPSIS if you go to the Google Scholar, right? And if you type the TOPSIS in the right search, so you will see that how many articles it is coming, 4,20,000. So just the recent data today, I just took this data. If I type the TOPSIS in the Google Scholar, I will be getting right the 4,20,000 articles related to the TOPSIS, right? So you can understand the importance of this TOPSIS, right? So various research papers are being published in the various areas with respect to the application of these techniques. So again, if I say right since 2021, so this is the data right in any time, right, means till now, right, articles with respect to the TOPSIS stands 4,20,000. But if I talk right since 2021, right, how many articles are published or how many articles right are related to the TOPSIS? So you will see that 70,000 of the articles are related to the TOPSIS. So you can understand this right popularity of the TOPSIS, and even right other methods are also equally right or comparably right popular. So what are the various steps that are utilized or used in this method? So first is the development of decision matrix. So we will take a numerical example also so that we can understand clearly each and every step or we can apply in our further work if it is uh, suitable. So first step is to develop the decision matrix. Second is to construct the normalized decision matrix. You will take one by one also. Construct the weighted normalized decision matrix. Fourth step is determine ideal and negative ideal solution. Fifth one is calculate the separation measure. Sixth one is calculate the closeness coefficient, and based on the closeness coefficient, we are ranking. This is the last step, is the ranking. That's our objective, right? To rank either the materials, or to rank the suppliers, or to rank the various locations, or to rank the various third-party logistic providers or service providers or other things. So this is a development of decision matrix. So what is a decision matrix, right? So there are certain criterias. So here the criterias that are mentioned is n number of criterias. C1, C2, Cj and Cn is a n number of criterias, and we have certain alternatives. So these alternatives is to be ranked based on these criterias. So you can understand like that we have so many cars. Car from BMW, car from Tata, car from Honda, and even from one supplier also, from one make brand, like Tata, we can have n number of cars, and there are various criterias like quality, cost, mileage, build, quality, safety, etc., etc. Now, right now our resources are limited, and we want to select as per which one to select. That is because each and every criteria is some of the criteria may be conflicting. If you want the high safety, high comfort, then the cost will be higher, but you are not able to pay, you are not ready to pay that much. Okay, so if even the things are, everything is okay, but the mileage is poor. If again the mileage is also good, but the service is very poor. So this is one of the crude example that I am giving, so that everyone can understand the importance of or understanding of this MCDM methodology. Now, what is happening? So based on each criteria, we are giving certain value to these alternatives, right? So this criteria one, corresponding to the A1, the value is let x11. Similarly, the x21 is the value given to alternative 2 based on the criteria 1. Similarly, this is for the ith one, for the mth one, the value is xm1, So this value is representing the value given for the mth alternative for the first criteria. So these values, this is a decision matrix, So decision matrix, how to develop the decision matrix? Who will provide the data for this? So who will provide the data for this is the experts. So the experts, we are we have to go, we have to either interview, or we have to send the questionnaires to the experts. Based on their opinion, we are collecting the data for these MCDM methodologies. Like if you have to do some certain analysis on the data, with respect to the manufacturing, the machine is giving us the data. But if we have to make the decisions, where the data is highly it is not objective data, there is subjective data, so we have to depend on the experts. So experts are providing that data, and based on their data, we are making this decision matrix. And these are the weights W1, W2, Wj, and Wn corresponding to each criteria. So just when we take example, it will be more clear. I'm just explaining the steps. So the rating, the scale that we may use for rating the qualitative criteria in case of the classical Topsis method. So this is the right scale or that we can use to rate the alternative based on a particular criteria: poor, medium poor, fair, medium good, good. So if for the poor if we convert it into the numerical, so for the poor we are giving it 1, for the medium poor we are giving it 3, for the fair we are giving the 5, for the medium good we are giving 7, for the good we are giving the 9, and intermediate value means 2, 4, 6, 8. If any alternative is between poor and medium, then we are giving the 2. If it is between medium poor and fair, we are giving 4, like that. We are giving the intermediate values. So it is like like if I talk about the safety of Tata car, right? Someone will say is a very good, someone will say is a very, very good, someone will say it is a fair, depending upon, right, his understanding or his experience. Okay. So that is the meaning, right? We are rating, right, a particular alternative based on that particular criteria. So this is for the qualitative criteria where the objective data is not available. But when the quantitative data is available, that the data with respect to the cost is available, then we will use the direct values instead of using any linguistic scale. Then the second step, once we have formed the right decision matrix, so 𝗕𝗏𝗄𝗃 is a element of decision matrix. So 𝗕𝗏𝗄𝗃 is representing the value for the ith alternative for a particular jth criteria, right? So this 𝗕𝗏𝗄𝗃 is to be normalized, right? So why we are doing this? So this 𝗕𝗏𝗄𝗃, right? This criteria may be the cost, the criteria may be, right, the distance, the criteria may be the quality, right? And the dimension or the unit of each and every criteria is different, right? And the values, right, may differ depending upon the unit that you are choosing for measuring that particular criteria, right? So this will result, right? So the value which are higher will dominate, will, right, influence the result, right? So to avoid that problem, what we are doing, we are normalizing or we are non-dimensionalizing the attributes or criteria. So the method that is utilized is for doing the normalization is Rij is equal to, so this Rij is a, right, normalized element of decision matrix. So Rij is equal to Xij. So Xij element of the decision matrix previous step. Then what we are doing for a particular, right, criteria, right, we are summing all the values corresponding to all the alternatives, right? So we are finding the sum of all the column, sum of a particular column, and we are dividing each value in that column by the sum of that particular column, right, to normalize that. So what we have done, so in these two steps, we have converted, right, Xij into Rij. So Xij is a, right, element of decision matrix, and this Rij is a normalized element of decision matrix. After that, right, what we will do, we will construct the weighted normalized decision matrix. So whatever the weights that we have for the criterias, right, like for the first criteria, we have the weight W1. For the criteria 2, we have W2. For the ith criteria, we have Wi. For the nth criteria, we have Wn. So what we will do, we will multiply each, right, criteria by its weight, right? So depending upon, right, someone wants to give more preference to the mileage, right? Depends in our life. Someone wants to give more, right, weightage to the safety while selecting the car. Someone wants to give, right, the weightage to the, right, service. So someone is choosing the Maruti Suzuki car and someone is choosing, right, the the Tata car, depending upon, or Honda car based on the engine, or if you have to go for higher segment, then Audi, BMW, even then also you have to go racing cars and those, right, highly, right, expensive cars. So it will depend. So accordingly, we are, right, putting the weights. Okay. So when the resources are not, right, not a problem, like in case of very expensive cars, then there is no meaning of making the decisions when the resources are limited. So whatever the decisions that we are making, right, in making under, right, resource constrained environment. Okay. So we will multiply, right, each, right, weight, each column by its own weight. So this will become W1 into R1, and this W1 R1 is nothing but V11. So we have represented the element, each element of weighted normalized decision matrix by V11 normalized, right? So this is added here to be added. Okay. So what we have done in the 3-step, we have Xij. This Xij is converted into the Rij, and this Rij is converted into the Vij. So this Rij is calculated, right, from decision matrix, step 1. This is calculated by normalizing the element of the decision matrix. Then this is calculated from normalized matrix by multiplying the weights of that particular element. So what we are doing, Vij is what? Nothing but a Wj into Rij. Okay, so it's very simple steps. Then we have step 4, determining the ideal and negative ideal solutions. So how to identify the ideal solution and how to identify the negative ideal solution. So it will depend upon what type of the criteria is there, right? Whether the criteria is of benefit type or whether the criteria is of a cost type. So criteria is of benefit type when we want to maximize it, like a quality, like a service delivery, right? That we want to maximize. Performance, we want to maximize. What are the cost criteria? The criteria that we want to minimize. Like your distance, we want to minimize. Distance of service center, right? The time of delivery, we want to minimize. Cost, we want to minimize, right? So these are the cost criteria, the criteria we want to minimize, the criteria we want to maximize, the benefit criteria. Now, so we have to find the ideal solution and negative ideal solution. So A plus is representing the ideal solution, right? So if the criteria, so J is representing the criteria. So everyone just keep in the mind. So this is a mathematics, right? This may seems difficult. So I will explain so it will be easier for everyone. So J is representing the criteria and I is representing the alternative. Okay. So what we are doing here, ideal solution, right, is a set of the values, right? So what is that? So for if the criteria is of benefit type, so benefit type criteria is represented by J, group of those criteria. A set of those criteria is represented by the J, and set of cost criteria is represented by the J dash. So set of the positive solution, how it is calculated for if the criteria is of benefit type. Then we are selecting the maximum value, right? Maximum over what? Over I, means maximum over all the alternatives, right? So for a particular column, right, we are finding the maximum of that column over each alternative, over all the alternatives, if the criteria is of benefit type, because that is a maximum value, right? That is the ideal value that you want, right? If a particular car is providing you the minimum that top safety, then definitely that is ideal solution for you among all those alternatives, right? Similarly, if the criteria is of the cost type, then what you will do? You will choose the minimum value over all the alternatives. So similarly, if the cost is our criteria, then we will select a car, or the ideal solution will be the car which is having the lowest cost. Now, what is the negative solution? Just opposite of ideal, right? If the criteria is of benefit type, if something is very poor, right, then it is the negative ideal solution for benefit criteria. If something is maximum, right, then it is the negative ideal solution for the cost criteria, right? If any company, right, is providing the very poor quality of cars, right? So what is that? This is a ideal solution, right, for the benefit criteria. If the cost of the car is very, very high, then it is a negative ideal solution for the cost criteria. So in this way, right, we are developing the ideal solution and negative ideal solution. So this J is representing the criteria and I is representing the alternative, and this J and J dash is a right set of benefit criteria and the cost criteria. After that, the step 5, what we are doing, we are calculating the separation measure. So how we are doing the separation measure? How each value in the column is deviating from the positive ideal solution and how each value is deviating from negative ideal solution in each column. Then what we are doing, we are summing up all the values across all the across all the criteria, right? So that is the meaning of ideal separation. Similarly, we are calculating the negative ideal solution, right? How? By taking the subtraction of the value with that negative ideal solution, by making it a square, by adding it across all the criteria, across all the alternatives, and that we are doing for each criteria. So there has to be one summation also here. So that is missing here. Okay. So when we will take example, it will be clear to you. So at the last sixth step, we are calculating the closeness coefficient. So closeness coefficient is calculated for each alternative, ith alternative. So similarly, this ideal separation and negative ideal separation Si plus and Si minus is calculated for ith alternative. Similarly, this closeness coefficient is calculated for ith alternative, and it is given by, right, this negative ideal separation divided by positive ideal separation plus negative ideal separation, and the value will definitely lie between 0 and 1, right? And which criteria you will be choosing, or which alternative you will be choosing? The alternative which is having the highest value, because on the numerator side you see that we have negative ideal distance, right? And if we want a particular criteria, right, the best criteria, then it has to be far away, right, from that particular, right, the distance, right? The ideal negative ideal distance would be maximum, right, and the positive ideal distance would be the lower one. So a set of alternative can now be preferenced, ranked according to the descending order of Ci plus. So the alternative with the highest closeness coefficient represent the best alternative. So the alternative which is having the highest closeness coefficient, right, highest separation distance, negative separation distance, right, ideal negative separation distance or separation distance, right, not ideal one, because the ideal one is the one. Then we are calculating the separation distance for each and every alternative. Okay, so the one which is having the highest separation distance or that ratio will be the part of this alternative ranking. Now take an example, right? So till now, right, I've just explained the steps involved, right, in this 𝗕𝗪𝗔𝗟 methodology. Now we'll take one numerical example to understand everything. So let for a company that wants to select its supplier, suppose the following criteria and the characteristics to be considered most important: the price, time of doing the project, quality, capacity to deliver large quantity, and the distance. Okay, so these are the criteria that we have identified. So based on these criteria, we have to select certain, we have to rank the supplier. So we have to identify the most suitable supplier or most few suitable supplier, right? So we have, in this case, the 4 suppliers are there, and we have these 5 criteria, right? So we have criteria. First criteria was the price, right? The price. Second one was the time. Third one was the quality. Fourth one was the capacity. And the last one is your so it is hanged, right? It's not moving. Just wait. So I will just again say, right, the PPT hanged in between.
Okay, sir.
Yeah. So hope, right, my PPT is visible to everyone. So right, your fifth. Again, what happened to this? Yeah. And the fifth one is the distance, right? So this is the distance here. So this was the price. This was the time. This was the quality. This was the capacity. And this is the distance. So now we have to identify what are the criteria which are the benefit type and what are the criteria which are of cost type. So the criteria that we want to maximize will be of benefit type. The criteria which we want to minimize will be of cost type. So we want to price to be minimized, right? We don't want the price to be higher, right? We want the price to be the lower, right? So that is a cost criteria and we are putting the negative sign for that, right? Similarly, time. We want to minimize the time of the delivery. So that's why it is also a cost criteria. We want to maximize the quality. So it is a benefit criteria. We want to maximize the capacity. That's why it is also a benefit criteria. And we want to minimize the distance. It is a negative criteria. So, right, the data that is available, right, for directly the data that is available for the criteria is criteria are the price, right, the time in the distance. This data is available to us. What will be the price that is quoted by the supplier? What is the time that is quoted by the supplier? What is the distance that is quoted by the supplier? And you know the distance already, not quoted. You know the distance of the supplier from your location. But the quality and the capacity, right? How much they are having, right? They may not have, right, any data for the capacity, like they have high capacity or very high capacity or low capacity, right? Like that type of the judgment is there. Then you will be using that 1 to 9 scale. And based on that 1 to 9 scale, right, you are rating that particular supplier, right? So similarly, right, for the quality also, if you're rating, right, one supplier 9, so it is very, very good. If you're rating another supplier, it is not so good or according to the scale, right? So in this way, right, we have developed the decision matrix. So for the price, for the time, for the distance, we have direct quantitative data is available with us. For the quality and the capacity, the data is not available, right, with us. That is available in subjective form. So for that, we have used the scale, right, for providing the rating. So that was the first step. So first step was to develop the decision matrix. Second step is to develop the normalized matrix. So what we will do in developing the normalized matrix, we have already seen. So what we will be doing? We are taking this column, right? We have to normalize this column, or the values in this column is to be normalized. So what we will do? We will make a square of each value. 80 square plus 75 square plus 72 square. And we have already seen the meaning why we are doing the normalization. And 65 square. Then we are summing everything and we are taking the square root, right? And we are dividing each element by this value. So this value is given, right, 146.40 for the first column. For the second column, it is 27.09. For the third column, it is 15.36. For the fourth column is 13.41. And for the fifth column is 377.62. Then we are dividing each value by its total. So in this way, right, we are getting the normalized matrix for each criteria. Normalized column for each criteria and normalized matrix as a whole. So after that, we have to develop the weighted normalized matrix. So to develop the weighted normalized matrix, what do you need? You need the weights of the criterias. Now how this weight will come? Again, you can employ any other, right, MCDM technique to evaluate or to calculate these weights, or directly, right, based on their experience, the experts may give you the weights, right? So once the weights are known for each criteria, right? So how the weights may come? The weights may be given by the experts, or they may be calculated with the help of experts and other MCDM techniques. So this is the weight for the criteria 1, this is the weight for the criteria 2, this is the weight for the criteria 3, this is the weight for criteria 4, this is the weight for criteria 5. So what we are doing simply, we are just multiplying each column or each criteria by its own weight. So the weight for the first criteria is 0.12, for the second one is also 0.12, for the third one it is 0.16, for the fourth one it is 0.16, and for the fifth one it is 0.5. So we are, right, just multiplying each column by its own weight, and these are the value that you will get after the multiplication of weight. So this is a what? Weighted normalized matrix. So what we have done, we have Xij decision matrix. Then we move to the normalized matrix Rij, right? We are talking about the each element in that matrix. Then we move to the Vij, weighted normalized matrix. Okay. So after that, what do you have to do? We have to identify the ideal solution and negative ideal solution. Now this ideal solution and negative ideal solution will depend upon the type of the criteria, whether it is a cost type or whether it is a benefit type. So if I go right here, so you can see here we already taken that this criteria is of cost type, this criteria is also cost type, this is a benefit type, this is a benefit type, this is also cost type, because this criteria was price, right? This was the time, this was the quality, this was the capacity, and this was the distance. Okay, so if we have to find the ideal solution, so ideal solution based on the price, what should be the ideal solution? The price should be the minimum as possible. So what is the minimum number here? In this column is 0.05. So I'm developing the set of ideal solution. So for the first column, the ideal value is 0.05, the minimum most. Then for the second column, it is again a cost type. The minimum value is 0.05. For the third column, the criteria is of benefit type. The high maximum possible value will be the ideal value that we want, 0.09. Then capacity also we want as maximum as possible, right? So it will be of maximum value is 0.1. Then this is again the fifth one or last one is the distance criteria, that is of cost type. So you want to have the minimum distance as much as possible, and ideal will be minimum most, that is 0.06. Okay, so this is a positive ideal solution. Similarly, you can make a set of negative ideal solution. So again, it is a very simple, right? So if we go the negative ideal solution for this, the criteria is of cost type, so the highest value will be the the negative ideal solution. The worst solution for the time, the worst will be the maximum one, 0.06. For quality, the worst will be the lowest one, right? The one that is providing the poorest quality is the worst, right? This is a 0.05. Similarly, the capacity 0.05, and similarly for the distance, the highest one, is 0.34. So this is we have got the set for the positive ideal solution and for the negative ideal solution. After that, what we will do, we will calculate so this is the same thing that I explained here. So this is a set of the positive ideal solution and is a negative ideal solution. So next step is your calculation of separation measure, right? So separation measure you have to calculate. So what we are doing, we are calculating separation measure, positive separation measure and negative separation measure for each alternative. For each alternative, we are calculating. For ith alternative, we are calculating positive separation and positive ideal separation and negative ideal separation. So how to do that? So it's very simple. So as the name suggests, separation. Separation means how far you are from the ideal solution. So what you will do, you will multiply 0.06, you will subtract this ideal one from this one, 0.06 minus 0.05, or let me erase okay. So what I will be doing, so this is the ideal value for let me use this color, so the ideal value for this column is 0.05. For the first column, I'm writing on the top. For this is 0.05. For this is 0.09. Or you can mark, there's no need, you can also highlight there, 0.1 and 0.06, right? So what you will do to calculate the separation? So you will subtract this value from this. You'll make a square of this. Similarly, you will subtract this from this. For the each alternative you will calculate, right? These are the alternatives. A1, A2, A3 and A4. These are the 4 alternatives. For each alternative, we are calculating the distance. How we are going to calculate the distance? 0.06 that I am calculating for the first one. 0.06 minus 0.05 ka whole square plus. Similarly, now this, how much it is separated from the ideal value? That is 0.05. I know it is 0, but I am putting it for the calculation. 0.05. Again, subtract this and make it a square. Plus, similarly, how this value is deviating from the ideal value? 0.09 minus 0.09 ka whole square plus 0.08 minus 0.1 ka whole square plus 0.34 minus 0.6 ka whole square. Like this we will do. We will sum them and we will take a square root. So in this way, right, we are calculating the separation from positive ideal solution. Similarly, we are calculating the separation from negative ideal solution. So next time what we will do, if we have to calculate the separation for particular alternative, then we will take all these values and we'll take all these values. You'll subtract the respective values, make it a square, do the sum, and again take the square root. So in this way, right, we will be able to calculate the positive separation, ideal separation, negative separation or separation measure, positive separation measure, and negative separation measure for each alternative. So this is for first one. There are 4 alternatives, so the 4 suppliers are there. This is for the second one. This for the third one. And this is for the fourth one. Okay. So this separation we have calculated, right, for each alternative for the ith alternative. Now next step was to calculate the closeness coefficient. Right, so closeness coefficient is negative separation divided by negative separation plus positive separation. So if we do for the first one, right, so what will be for the first one? CC1 will be 0.05 plus 0.05 plus 0.28. Similarly, we can calculate the CC2, CC3 and CC4. And the one with the highest weight will be the one with the highest value of CC will be the best alternative, right? So if we do the calculation, this is 0.15 for the first alternative, 0.22 for the second alternative, and we'll do for the third and fourth, it is a 0.82 and 0.55. So highest one is for which alternative? For the supplier 3, right? So it is ranked 1. After that 0.55, so it is ranked 2. Then after that 0.22, so it is 3. Then after that is 0.15, it is ranked 4. Okay. So in this way, right, we can use the TOPSIS to solve the decision making problem with respect to the supplier selection, right? So like in case of the semiconductor industry, right, if you have to select the material, right, based on certain, right, the factors that we have seen mentioned in the paper, melting point, right, or coefficient of expansion or something else, right, that is a technical part that will vary from industry to industry, right? So once you know all your criteria, you know all the alternatives, you can apply this methodology to, right, find the best alternative. So this, right, classical TOPSIS or simple TOPSIS. Now we also have, right, the concept of fuzzy MCDM approaches, or if we talk about this fuzzy TOPSIS, right? So you have, right, in the examples that I took in the starting, right, with the decision making problems, you encounter this word fuzzy, right? So what is this fuzzy? fuzzy is nothing but is representing the vagueness, right? Sometimes we are saying this apple is red. It is red. So, right, this apple is red or not? Again, right, red, right? So again, it is a vague statement. Someone will say it is red. Someone will say it is highly red. Someone will say it is not red, right? Or if I am saying that he is running fast, he is running fast. Again, let very fast. He is running very fast. What does it mean? When you will say he is running very fast. Okay, so this is again a vague statement, right? It is not clear, right? Again, high quality, poor quality. What is the meaning of high quality? How will you give that number, right? So to take that vagueness into account, right, we are using the fuzzy approach, right? If I say if someone is going with the speed of greater than 100, is driving fast, is driving very, very fast or doing the rest driving? If someone is driving greater than 100 km per hour, or let regional value, let 200 km per hour or 150 km per hour, he is right called the rest driver. Now, the one who is driving with 199 km per hour, is he not a race driver? Yes, he is also a race driver. The one who is also driving with a 0.1 is of course a race driver. But the 199 one is also a race driver, 198 is also a race driver. But the degree of membership, so we have one concept called degree of membership. So one who is driving with 200, we assign the degree of membership function as a 1, right? And one who is driving with 199, we assign a degree of membership as a 0.99. Okay, so we have crisp set, right, where we know that we have only the one term values, either they are inside the set or not. But here, we have another term, the values are defined with their membership functions, right? So to take into account the vagueness, like the vagueness here is that I am saying that those who are driving greater than 200 are the race drivers, but those who are driving is 199 is not a race driver. How to find the set of those drivers who are the race drivers, right? So the one who is driving with the 200 is having the membership function of 1, or who is driving with the 199 may have a membership function of 0.99. But he is also a race driver, but the membership function is reduced, right? Associativeness with respect to that is reduced. So the fuzzy set theory is combined with the Topsis methodology to work in the uncertain and vague decision-making process. This allows decision makers to integrate unquantifiable information and incomplete information in the decision-making process. The fuzzy techniques assigns the comparative importance of the attributes by means of the fuzzy number rather than a numeric value. So instead of providing a one numeric value, right, we are providing, there are various types of the fuzzy number. We have triangular fuzzy number, right? We have trapezoidal fuzzy number, right? So if we have generally use a triangular fuzzy number, so what we have 3 numbers to represent that particular situation. So L, M, N, right? So let's see what is the meaning of that. So what are the steps? Again, the steps of the Topsis will remain same. Step 1 is the development of fuzzy decision matrix. Step 2 is the computation of normalized fuzzy decision matrix. So what has come now? Fuzzy part has come. Fuzzy decision matrix has come. Compute the weighted normalized fuzzy decision matrix. Compute the fuzzy positive ideal solution and fuzzy negative ideal solution. Compute the distance from each alternative to FPIS and FNIS, fuzzy positive ideal solution and fuzzy negative ideal solution. Compute the closeness coefficient for each alternative and rank the alternatives, right? So again, let's see, right? So again, the first one is development of fuzzy decision matrix. So to understand that, right, each value is of fuzzy type. What we do, we put the tilde over that value is representing the fuzzy value. And fuzzy value is nothing but it is having the 3 numbers, triplet, L, M, N. Instead of assigning one number, what we are doing, we are assigning the 3 number. And these 3 number, right, are having the relationship, triangular relationship. So this is the L, this is the M, and this is the N. It may be any triangular relationship. It is not like that. It is always like that. It may be depend this also. Okay. So if I am saying the value is that the quality is very good. Quality is very good. So I am assigning one triplet corresponding to that, right? If there is a middle number for that, the membership function is 1. For the lower one, it is 0, and for the next one, it is 0. If take an example, if someone is driving with the speed of 200, right? The same example, right? If someone is driving with a speed greater than 200, he is driving very fast. He is driving very fast. We are discussing that we have speed very fast, right? Very, very fast and extremely fast. Okay, so very fast, the speed if it is beyond 200, it is very fast. But the speed that is also 199 and 209 is also very fast. But how to take that into account? So what we do, we assign one membership function. So corresponding to 100, the membership function is 1. And corresponding to 199, the membership function will be something as per this relationship. And our L may be like the 190. And this may be like the 210. Beyond the 210, that may fall under the very, very fast category. Or below 190, it may fall under fast category. But for the very fast, instead of assigning only one number, 200, I am assigning a triplet, 190, 200, and 210. And with respect to that, there is a corresponding, right, Y value, right? That Y value is nothing but a membership function. Okay. So now, right, what type of the scale that is used to rate the alternative based on a particular criteria, right? So this is a scale that may be used for rating the rating the alternatives based on the particular criteria. So you can see here, this is a triplet. This is a triplet corresponding to a particular fuzzy number. So if there is a not important, I am giving it 113. For less important, I am giving it is 135. For fairly important, it is 357. For the important, it is 579. And for the very important, it is 799. Right? So there are varieties of membership functions are there. Again, for the triangular membership function, you can have the various values, right? As per the relationship, triangular relationship that is available in the literature. Okay. So that is based on this scale, right? What we will do, we will do the ratings. Again, we'll take one example. I know the time is going to be, so I will just go a little bit of fast, okay? Because already we know the steps, okay? So we'll go directly switch to the examples to understand the things, okay? So second step is the if, right? Now the question may come to your mind, right? We are not generally depending on only on the one expert, right? We may consult a group of experts, right? So and it will definitely provide, right? Because the different experts have different mindset, different opinions, different experience. So if we are taking the input from the various experts, then how to aggregate those inputs? So for aggregation of inputs, let Xij is any fuzzy input for the kth expert. This fuzzy input is represented by the triplet Aij, Vij, and Cij, right? With respect to, right? So if I have to do, right, for a particular criteria, right? If I have to aggregate the fuzzy rating of ith alternative with respect to the jth criteria, like I have this alternative and this is the criteria, right? Someone has said very high or very good. Someone has said let the good, right? This is the expert 1, right? This is the expert 2 who has said the good, and the expert 3 has said again the very good. Now how to combine these three, right? So for the combination of combining these or for aggregating the fuzzy input, we again use the one formula, right? So the first, if 3 or k experts are there or k inputs are there, so the aggregate input Aij will be the minimum of k, Aij k. Means we will take the minimum of all the Aijs, right? All the Aijs provided by the expert. Similarly, the last number or last triplet will be Cij. It is maximum of all the Cijs, right? So like we have A11, A1, right? A11, right? A for the jth criteria, 821, A31, right? Right, is for the expert one, right? K is 1. Similarly, right, we may have A112, or let even right, if we take the first criteria itself and first alternative, right? So you can make A11 itself. So this representing that only. So A11, right? Right. So this A and this is a B, right? So we are representing the triplets by A, B, C, right? A, B, C. So this is again A, this is a B, this is a C, right? So I think let me just erase this. So I think it's some. Yeah, so let the first expert has given the right its rating as A11, B11, C11, right, for the first criteria and first alternative, and it's given by the first expert. Similarly, the A11, AV11, C11 given by the second expert. Similarly, write any value A11, B11, C11 given by the third expert. So how to aggregate that we are discussing. So what we will do to aggregate this number, first number of the triplet, what we will do, we will take the minimum of these three. Similarly, to find this number, what we will do, we will take the maximum of these three. And for finding the minimum number, we will just do the normal average. Arithmetic average we will do. So in this way, we can aggregate the thing. So after that, what comes? The normalized fuzzy decision matrix. So what we are doing, normalization is done, right? To normalization, what we are doing, if the criteria is of benefit type. If the criteria is of benefit type, what we are doing, we are finding the maximum value of the Cij over all the i's. So remember, I is representing the alternative and j is representing the criteria. Okay. So what we are doing, we are finding the maximum value, maximum of Cij for a particular criteria over all the i's. Then we are normalizing, right, the values in a particular column that we did in the classical topsis, right? So we will divide all the values by the Cj star if the criteria is of benefit type. If the criteria is of cost type, what we are doing, we are finding the this is like they have written here A, so let I am putting it AJ minus, right? Is a right on the top is a hyphen, or you can say that. So there's a minimum of Aij, right? So you are considering all the Aij, right? You are finding the minimum over all the i's, right? So you're taking on the top and dividing by Cij, Wij, and Aij. Now, why we are doing this, right? You may be confusing, right? Sometimes you are taking A, B, C. Now we are taking here C, B, A, right? Because you have to remember that L has to less than M and has to less than N, right? So to maintain that relationship, right? These calculations, these are the operations done on the fuzzy number. So there's a fuzzy arithmetic, right? So fuzzy operations are there, like we have normal operations. Similarly, we have fuzzy operations, right? So this is a part of the fuzzy operation that we have already not, of course, not discussed here. So that may be the problem, right? But you can go through those fuzzy operations, then it will be clear, right, how the things are done. Okay. Then after that, what we are doing, we are finding the weighted normalized decision matrix. So we are multiplying it by the weights, right? So what we have done, we have developed the decision matrix, fuzzy decision matrix. Then we have developed the normalized decision matrix, right? We are putting the tilde now, right? Then we have developed the weighted normalized fuzzy decision matrix. Okay. So again, the same way, what we will do, we'll do the calculation for fuzzy positive ideal solution and fuzzy negative ideal solution. So how to find the fuzzy ideal solution. So to find the fuzzy positive ideal solution, what we are doing, we are taking the third component, right? Third component we are considering and we are finding the maximum of that, right? Then that will be the part of positive ideal solution. Fuzzy positive ideal solution. Ideal solution is the maximum value. And out of LMN, which is the highest value, N. And we have, right, so many criterias, right? For each criteria, we have so many N, right? Then among all the N, we are finding that maximum value, that will be the fuzzy positive ideal solution. Similarly, what will be the fuzzy negative ideal solution? You find the minimum. Take the first component and find the minimum of all that. Okay, then it will be your negative ideal solution. Next step is you have to compute the distance from each alternative to FPIS and FNIS. Okay, so again the same way. Now how to calculate the distance between the two fuzzy number, right? If the fuzzy number is x1, y1, z1, and the fuzzy number is x2, y2, z2, or L1, m1, n1, and L2, m2, n2, or a1, v1, c1, a2, v2, c2, any right nomenclature can be followed. So to find the right distance between them is x1 minus x2 का whole square plus y1 minus y2 का whole square plus z1 minus z2 का whole square divided by 3. So this is a way, right, how we will calculate the distance between the two fuzzy numbers. So after doing the fuzzy number calculation for distance separation measure, then we will calculate the closeness coefficient. So closeness coefficient is given by, right, this negative separation divided by positive separation plus negative separation. This is a positive one, di plus. Okay. So after that, again, the alternate with the highest closeness coefficient represent the best alternative. So let's take an example quickly, right? So there's a, you have to select a supplier. Right now, everyone is talking in the supply chain, you know, that sustainability. Everyone is talking about the sustainability, right? And it has three, right, pillars: environmental sustainability, right, social sustainability, and economical sustainability. So whatever the organization is there, right, it has to carry out its operation so that it does not cause any harm to the environment, it does not create any problem to the society or employees or the social work or the workers. That is the meaning of social criteria. Similarly, the economic criteria, if they have to sustain, they have to earn the profit continuously, right? So based on these three criteria, if there are three suppliers, how to select them, right? So this may be the one of the problem, and this can be, right, again solved with the help of the Topsis or Fuzzy-Topsis methodology. So we will just demonstrate here quickly the Fuzzy-Topsis methodology, right? So the company, right, or the expert have identified these 12 criteria, right? So the first criteria is the cost, second is the quality, third one is the on-time delivery, fourth one is rejection rate control, fifth one is toxic chemical usage control, sixth one water consumption control, seventh one energy usage control, C8 pollution control, CN9 restriction on underage labor, right? So these are the part of the social criteria: restriction on the long working hours, human rights care, safeguard mechanism for workers, and these are, right, with respect to your environmental criteria, right? And these are with respect to your economic criteria, right? So based on these criteria, right, we have to rank alternate suppliers, right? So let how many suppliers are there, we will discuss. So there are three suppliers, S1, S2, and S3. This supplier has to be ranked based on these 12 criteria. So what we have certain scale, that is a fuzzy scale. So fuzzy scale, right, in terms of the fuzzy number. So we have, right, two separate scale. So first scale is for calculating the weights of the criteria. Like in the previous classical Topsis, we directly put the weights. But as I told you, we have to, right, take the help, right, of again certain inputs from the expert. Directly you can take that input, or again by applying indirectly take input from the expert and convert into the weight, or directly in the form of the weight also you can take. Okay, so this is a fuzzy number, right, which is used, right, for calculating the weights of the criteria, and these are the, right, the fuzzy number which is used for rating purpose whenever we are rating the each alternative with respect to the criteria. So what we are doing, let this is a criteria, three experts are consulted. We have 12 criteria, right? And we have three suppliers. So for supplier 1, for the first criteria, the expert 1 has rated high, and very high. Similarly, let for the criteria 9, for the supplier 2. For the supplier 2, he is ranked medium, medium important, or highly important, depending upon the scale that is there. Right? So this is a scale. This is a very poor, very, very low, poor, right? Medium poor, average, high, and very, very high. So depending upon that, this rating is given. Right? This expert is giving his rating. Now, these are the three inputs. Three ratings given by three experts. Now we have to aggregate that. We have to bring it as a one number. So we will use the aggregation method. So this is the aggregation method that we have discussed. So what we will do, let someone has given, right, let these three. Someone has given that very low, and at low I'm just taking, and another one has given the average. So what we'll do, how we'll do the aggregation of these three? We'll take the minimum of these three. What is the minimum of these three? 0. What is the maximum of these three? Is 7. What is that? We'll take the average of 3. 1, 3, 4, 4 plus 5, 9. 9 by 3, 3. So this is the average. So in this way, right, we have done the aggregation. Right. So in this way, right, we will do the aggregation for each rating, right, for corresponding to particular criteria and supplier. So these are the aggregate values are mentioned here. So after that, what we will do, we are doing the normalized, we are doing the developing the normalized fuzzy decision matrix. So what we will be doing here, we have to do the normalization. So we have to find how the way of normalization. So how we are doing the normalization depends here, right, depending upon the whether the criteria is of benefit type or whether the criteria is of cost type. So if the criteria is of benefit type, we are finding the maximum value. Let we take this example, right? So if we take this example, that this example we take. Okay. Now the criteria is mentioned here, right? So these are the the numbers for a based on particular criteria for 3 suppliers. So what we have to do, we have to normalize these 3. If you have to normalize these 3 out, you differentiate, right? In the previous example, supplier was on this side and on the top was the criterias. Now here we have in this example criteria mentioned here and supplier mentioned on the top. So you can write put in any way. So but you have to remember the calculations. Now the calculation will be done row wise, right? So if you have to normalize each criteria, right, each value under each criteria. So if you have to normalize this, so what we are doing, these are all the criterias. First criteria is cost. So this cost is of what type of the criteria? Cost type of the criteria. So what we will do, we will find the minimum of AIJ. So what is the minimum of AIJ? So this is the AIJ for this, AIJ for this, and AIJ for this. So what is the minimum of 5, 3, 3? 3 is the minimum, right? So what we will do, we will take 3 divided by, if I do the normalization for this, I'm doing the normalization for this, then 3 divided by 10, right? 3 divided by 8.33 and 3 divided by 5. So in this way, right, the calculations can be done. After the normalizations, right, what we have done, we have calculated the weights. Weights of what? Criteria's weights. In the previous example, we took the direct weights. Now here we have taken the calculation is done for calculating the weights. So again, they have used again fuzzy scale, and 3 same experts are consulted and they have provided the ratings. And again, this is the aggregated weight that we have received for against each criteria. So once we have received the weights, and so we have 𝗙𝗧, right? Normalized input. Normalized input is converted into your decision, right? Input is converted into the normalized fuzzy input. Then it is to be converted into the weighted normalized input. So what we will do, we will multiply by the weights, right? So we have got the weight for the criteria 1. So what is the weight for the criteria 1? This is the weight for the criteria 1. So what we will do, we'll multiply this by which number? By this number we will multiply these 3 numbers, right? So we'll multiply these numbers by the weight of the criteria 1. Similarly, we will multiply these values by the weight of the criteria C11, right? So like that we did. Now, how to multiply the two fuzzy number? The same way, L1, M1, N1 into, right? So you multiply the two fuzzy number L1, M1, N1 and L2, M2, N2. So the multiplication will be L1 into L2, M1 into M2 and N1 into N2. Simple, straightforward. Right, after that, what we'll do, we will calculate the fuzzy positive ideal solution and fuzzy negative ideal solution. So what we are doing, we are finding the maximum, right, over all the i's, right, for the third component, right? So if we talk about here for the criteria 1, right, we have to find the positive ideal solution. So consider the maximum value, right? The maximum value lies at the third triplet number. So maximum of that maximum is 1. Minimum is what? For finding the minimum, you have to consider the first one. So maximum will be the 1, minimum will be the 0.15. Similarly, for this criteria C9, what is the maximum value? Fuzzy positive ideal solution, maximum of these three, 0.9, 0.81, 0.90. What is the maximum? 0.9. We have to find negative ideal solution. Fuzzy negative ideal solution, take the minimum of these three. Minimum of these three is 0.09. So like this, we are calculating this. After that, we are calculating the right distance in the same way as we have discussed, right? So we are just, how we have already seen, right, how to find the distance between the two fuzzy number, right? So L1 minus L2 का whole square plus M1 minus M2 का whole square plus N1 minus N2 का whole square. Divide by 3, right? Then we'll take the square root. Okay. Then we are calculating the D plus and D minus. Then we calculate the right closeness coefficient and we can rank them. So this is the right way how we can do the calculation, right, for the fuzzy topses. Hope, right, this is clear to me. Right, I know that second example was a little bit fast, right? So now you see, you may thinking, right, this require a lot of right. Let me just share once again, right? So we can do all these calculations through, right, Excel also, right? We can prepare the Excel, right, for each and every, right, MCDM approach. So let this is for this is a template, right? Right, in Excel I have developed for the classical topsis, right? So these are the steps, right? So if you again, if you add more columns or if you change the value, automatically everything will be calculated, right? So this is a template, right? We have just put certain formulas, like this is a decision matrix that we have to provide. Then we have to provide certain formulas here for normalization, right? And similarly, you have to put certain formulas for finding the weighted normalized matrix. So again, the same, some formulas, right, for doing this D plus, right, or D minus stuff that we have done, separation measure. Then we can do for the closeness coefficient. Then finally, we can do the numbering. So like that, we can also develop for fuzzy topses and for other MCDM approach also. So I think I would like to end here. And if you have any questions, right, please feel free to ask me. So thank you for patience hearing. Hope you got something.
Thank you, sir.
Yeah.
Participants, do you have any questions for sir? Hello, dear participants. Any questions? Any questions, please? Okay, I think there is no question. So thank you so much, sir, for your insightful and engaging talk. And thank you so much for your time and effort you have shared with us today. Thank you so much, sir.
Thank you, ma'am. Thank you, ma'am, for your opportunity. Thank you. Thank you, everyone, for patient hearing. Thank you. May I leave, ma'am, now?
Yes, sir.
Thank you.
Hello, Vikas Tavir, sir. Are you here?
Yeah, I'm there. Can you hear me?
Thank you so much, sir. Yes, sir. Yes, sir. We can hear you. Sir, namaste, sir.
Namaste, namaste.
Okay. So, welcome, sir. So, this is our 10th session of Frontiers in Semiconductors and Functional Materials 2025. So, as you can see on your screen, this is Vikas David, sir. And let me give a short introduction of him. So Vikas David sir is the Senior Director for Value Engineering in the Semiconductor Products Group of Applied Materials. He has a diverse range of experience in the electronics industry through various value chains, including PV, solar, and semiconductors. He spent several years at Texas Instruments in several international locations, and then 4 years in a leadership role in a solar startup in USA that culminated with an acquisition by Applied Materials 11 years ago. After 18 years abroad, he returned to India and helped drive India operations, including the supply chain initiatives from India. He currently drives the Asia engine to look at value for the business unit, and he holds an engineering degree in electronics and an MBA from the University of Texas, Dallas. Sir, are you currently joining from USA?
Yes, I'm in Boston right now.
Okay, so what's the time then?
It's 9 o'clock in the morning. It's very comfortable time.
Okay, sir. Okay, sir. So thank you so much for joining us, sir. You may share your screen.
Yeah, I'm trying to share the screen now. Can you guys see my screen or not yet?
Sir, we can see your camera. Sir, in your toolbar, there must be a share
Yeah.
button.
I'm doing that now.
Yes, sir.
Now?
Yes, sir. It's visible. Sir, please make it full screen.
Yes. I will do that. Right. So, good evening, everyone. I know there were more than 100 people online. So if you can, I'm not going to show too many slides, and I'm not going to definitely talk any equations. I'm done with all that more than 20 years ago. What I wanted to share with you all is just to give you all a full understanding of the value chain in semiconductors and show that as India, under the leadership of Prime Minister Modi, tries to become a significant player in semiconductors, where the talent requirements will be, how diverse those talents are. Somehow, so what I'll do is I'll give a key introduction. I'll talk about what it means to be a product company. We'll talk about the value chain, what are the opportunities, and then I cannot leave without telling a little bit about Applied Materials India. And then we'll have a little bit of summary. The other thing is, anytime you have questions, please stop, raise your hand, ask the question, because this has to be an interactive session. It's more practical experience from the industry, definitely nothing from the textbooks. Okay? Can we proceed?
Yes, sir. Yes, sir.
Okay. So one of the things that all of you may have heard in time and again, everybody, whether it's in semiconductors or the technology field, is the $1 trillion market for electronics by 2030. Now, what does $1 trillion market mean? It means everything that uses electronics, semiconductors, that whole market, whether it is an EV or a PV or mobile phones, computers, data centers, everything. And you can see from this, right? And I have had the privilege of being in this industry right from 1985. So you can see I've been there almost from the beginning of this industry when we started looking at personal computers. I used to work in Wipro those days, where we used to build the personal computers, the 286, the XTs, 286, 386 Pentiums, long time ago. Then we came into the era of mini frames and mini computers. And actually, they were there even before PCs. But then you started getting into the mobile computing from BlackBerry. I myself was a big BlackBerry fan. I had a BlackBerry till the company finally told me, no, you got to move to iPhone. We are not longer supporting BlackBerry. But really, BlackBerry started putting so many things in the hands of the people. You could now do things in the hand without even opening a laptop. Big change. And then, of course, all of you are aware, Apple brought in the iPhone, where we became an app-based mobile phone. So you started generating apps for so many things that we use today. The next era was in the cloud. That was a big inflection, right? Suddenly, you did not have to store anything on your servers or hard disk drive. You could store it on the cloud, and you had private cloud, you had public cloud, you had all these services. Amazon, who nobody knew could be in technology, became the leader in web services. And then we had, of course, Microsoft, Azure, and then Google Cloud, and so many players coming into the play. Now look at 2022, we are at 573 billion. This year we'll already be at 640 billion. Minimum, maybe even more. And now you can see the buzzword of everybody talking is AI. So if you look at it, should not be anybody on this call who has not been impacted or has heard or talked about the potential of AI. This is the biggest inflection. I was in a talk with Jensen Huang last week, where he was invited to Applied Materials, and his message was so simple. So far, we had tools of IT, whether it was a laptop or a phone or a car that had electronics, but a human being went in. What we are replacing now is to put the intelligence there. And the simple example he gave was the automatic driving car. And you'll find those in several countries now, especially from Google's taxi, driverless taxi, Waymo. So what has happened now? The intelligence has moved where the car comes to you. You don't have to go and sit and drive the car. Just think about this as a concept across so many different things in all aspects of life. That is what AI power is going to change the world. And his message was two messages he gave. One, AI will not replace jobs, or it won't replace you. AI will replace you with people who use AI. Your job will go to somebody who's using AI to be more productive. So if you look at this chart, right, it shows how powerful AI, the semiconductor industry is growing to support all these things, whether it is the data centers, whether it's edge AI, IoT, robotics. China has taken such a large lead in robotics, EVs, electric vehicles, renewable energy. The whole industry for semiconductors is now driven by what we call as performance at area cost and the power. We need more power, we need high performance, but we need it to be low power. It has to consume the power consumption has to drop. So the die size, what we call in semiconductors, the size of the chip keeps increasing, your performance increases, but the power consumption drops. Understand this one thing, that the amount of power that these data centers are going to require at the current power consumption will make things very, very difficult for other industries. Hence, the focus on how do we develop semiconductors and electronics at lower power consumption. So your net power usage doesn't go up, but we are able to do all these things. Any questions so far?
Any questions, participants?
Okay, good.
I think no questions, sir.
All right. Let's move on. Now I'll move on to how an ecosystem gets built. Okay. You can see here any product company, and this can be any product. Don't consider, don't distinguish. It can be making a pen. It can be making a aeroplane. Any product company, there are three aspects to it. You have to design the product, you have to manufacture the product, and you have to service it. And service could include installation or could be only servicing. Very, very critical is how do we design products to solve customer problems? Products that are going to make life easier, improve productivity, add value, that comes right from the beginning. Every product company always goes and looks at what did not work. Everybody has a large R&D budget. From the R&D, there are many, many ideas that don't work. You've got to take the lessons learned from there, what were the failures, and incorporate that in a new product. And the third part that I always insist is during product design, you have to design a product that can be manufacturable at high quality, at low cost to make it affordable. So all these things get incorporated in product design. Now, what happens in product manufacturing? In product manufacturing, your focus is on doing it right first time. You have to have very good partnerships with your suppliers, extremely close partnerships with your suppliers. Because if you don't work with close relations with your suppliers, you'll have non-conformances, you'll have quality rejects, you will have yield problems, you will have delays, all those things come. And very important is, as you can see from the arrow, you have to keep giving feedback for making improvements. That feedback goes back to the product design team that, hey, when you did your design for manufacturing, you did not consider this. And this loop has to continuously be ongoing for a successful product company. The third aspect, which I think is the most important, is how do you make your customer happy? To make your customer happy, you've got to make sure your product works, it gets installed. Now, let's take the case of a phone. Now, you don't need to, when you buy the phone online, they have made it so simple for you to switch it on and download everything. If you went back to the phones that we were sold 20 years ago, you had to go to the store and they had to download everything and customize it for you. But now anybody who has bought the phone in the last 7-8 years online, either through Flipkart or through Amazon, you get it home and almost a baby can switch it on and get it functioning within a few minutes. The service people are the first ones to interact with the customer, whether it's answering their questions or servicing their products or installing the products. It is very important to make sure you're capturing inputs from these people to make improvements, because they are talking to the customers. They are your greatest source. It is not the marketing people. The marketing people are talking to sell. The service people are talking to you to solve your problems. So the feedback from the service people is very, very critical. Also, when the service person is talking to customer, the customers, whether intentionally or by unintentionally, tell what your competition is doing. If you're not good in something, they'll be very upfront. This competition, this competitive product does this company does this. So it gives you a good insight into what is happening with the competition. All these three aspects of the stool are very important to keep the stool stable. Has anybody tried to sit on a stool that is unbalanced because the legs are not proper or the floor is not even? You can topple, right? That is the intent of showing a three-leg stool. Any one of the legs is not firmly on the ground at the right level, your whole company will be at risk. Your whole product will be at risk. So for the stability of the product, just like how a stool, for it to be stable, you need three legs and you need it to be on a good even surface for it to be stable, so that when you sit on it, you're comfortable, you're not going to topple. Make sense? Any questions, guys?
Any questions? I think no questions, sir.
Okay. Moving on. Now let's look at the value, right? And I'll show 2-3 slides on this. In 1985, when I graduated from engineering, there was only one semiconductor company that had just started operations in India. That was Texas Instruments. So the whole concept of electronics design, what we had studied in school, was, okay, you work for a company like TI and do chip design. Over the years, as we went into the 1990s and 2000s, because of the talent we had in India, we had lots and lots of chip designers. And what did it require? It required a computer. It required a UPS at home to be able to do those designs. And electronics knowledge. So India had plenty of that. We had a lot of people very good in electronics, who studied electronics, who understood how chips works, who understood Boolean algebra, who understood transistors. So the design industry flourished in India. Unfortunately, that is what everybody in the universities and colleges started looking at. In parallel, the software industry took off in India. Now, software is a big part of making a chip. So that fueled the expansion of design engineers in India. 20% of the world's semiconductor designers are in India. Every company that makes chips, and I have only 3 listed here: NVIDIA, Qualcomm, AMD, and there are like maybe 1,000 companies. Almost every company has a presence in India in design. But semiconductor is more than just designing the chip. And I'll show another slide which will explain this more. But it starts from basic research in universities and research consortiums, where you're looking at what the application should be and what sort of transistor functioning is required to reach that application. Now, the application could be as simple as a watch, the timer on a watch, or it could be as complex as making a car work autonomously. So some concepts get designed there. Then you get into the IP and design. This is where the chip design companies come into play. They take this fundamental research, and the next slide will show you a little more details, where you'll use the software developed by several companies to enable chip design and come with a chip design. Now, when you're looking at chip design, you have some performance metrics. For meeting those performance metrics, you need to work closely with the foundries, or what we call as independent device manufacturers, companies like Texas Instruments, Intel, Samsung. That means, what does that mean? It means that your chip design has to be made manufacturable. If you remember my previous chart, you have to have design for manufacturability. So that becomes, because you got to have the manufacturing technology to support what you want to do. You want to design a chip with the lowest power, highest performance. Can it be manufactured? That's how that partnership has to work. Then it comes to the manufacturing of the wafer fab, where you have a 12-inch wafer, 8-inch wafer, 6-inch wafer made from bare silicon, where you're creating the transistors, the diodes, the capacitors through multi-stacking. Because now we have become so complex, we are working at Armstrong level. That is done by companies like Intel, Texas Instruments, Samsung, Micron, TSMC, a lot of them. Once the wafer is fabricated, it goes to what we call as assembly and test. And for assembly and test, we have a lot of people. A lot of the companies like TI and Intel have their own assembly and test, where the wafer, the chips from the wafer gets cut into individual dies and a final IC is made. Those get shipped to the end users of those chips, which is the PCB assembly makers of companies like Apple. So Apple now, to make the phone, they have to buy these chips, put it on a PCB, which goes into your mobile phone. So this is the high-level value chain. And for India, remember the two aspects. We have, like I said, we have the 20% of the designers. We have great universities and research associations, and we have 1.4 billion people. It's a lot of consumers. What we don't have is in between. And that is what the country is trying to establish. We have now 10 projects approved by Government of India. Let us spend a little more time, which is a lot more detail in this, on the same topic. You saw here, let's start from the design IP. You have companies like ARM that have the intellectual property for the base design. You have to use the electronic design software that companies like Cadence, Synopsys has done to start designing the chip. The people that design the chips are companies like Broadcom, NVIDIA, Qualcomm, AMD, you name them. So what they are doing, they are taking the software from the EDA companies. They are using the base IP from companies like ARM, and now they are developing their own. I don't know how many of you have followed, but Google just announced 2 weeks ago their AI chip can be used by many companies. Suddenly, Google being already such a high valued stock, their stock price went up even more. So this is the designing of the chip, and they have to work, like I explained, with the manufacturing companies. The manufacturing companies like TSMC will tell the technology nodes to the designers. If you can follow my arrow. Now, companies like TSMC require equipment and technology. And that's when they come to companies like us, Applied Materials, Lam, ASML, for different nodes. Now, a complex chip today takes around 6,000 steps. It is that complex. And just see how well all have to work together. If they don't work with the right manufacturing partners, their manufacturing yield will be low. They will not be able to make money. It won't work. If they don't work with companies like us, they will not be able to provide the technology required by the product companies. So all four have to work closely with each other. Now, once the wafer is completed, now even before that, you have all these materials, the raw materials that required to go into the fabs. Very, very important. And these are very high purity raw materials. So you got to have, there's a value there where to provide the right raw materials to the companies like TSMC. After you make the wafer, let's assume that all these 5 blocks that I showed, the designers, the IP providers, the EDA providers, the equipment and technology providers, the raw materials and the foundries or IDM all work together. After that, it has to be tested for making sure that you're getting the output of the electronic output that you have designed it for. And there is a test. This test is done at wafer level itself. So whichever die or individual chips which are good, they will only go to the next step. The ones that are not good get marked out, like cross marked. So when you're going to the next step of assembly and packaging, that time you're only making packages of the good systems. And that's where the assembly test and packaging, which is now packaging, is another big industry, billions of dollars worth of industry, where because you have gone three-dimensional. So companies like Amcor, TSMC itself has a packaging, ASE, TI has their own packaging, Intel has their own packaging. There is a test done after the assembly package is done to make sure that it is going to give the performance. And you can see here all these companies that do the packaging work. Texas Instruments, Samsung, Micron, etc. So many companies. So this is the final chip that goes to the consumer electronics or to the industrial electronics companies, which use these semiconductors to make the tools, whether it's a data center, whether it's a mobile phone, whether it's a EV vehicle or anything. So this is really how we make sure that the whole ecosystem is understood. And now you'll be able to understand that it's not only the design, but there is so much more to create an ecosystem. The last country that there were several, it went in phases. Of course, US and Europe were the leaders way back in the 80s and 90s. When I moved to US, I worked in Texas Instruments. They did not have so many factories outside. They had some assembly test factories in Singapore and Japan. Japan itself also had a lot of fabs. Then you started having foundries. These are foundries that can do for 10 companies. So the capital they could invest was much more because they are now spreading that capital over multiple companies. So that's how that ecosystem grew. If it went from US, Europe, Japan to Korea. Korea saw a big boom in their semiconductors. Taiwan was there. The history of TSMC is very interesting. You all should just Google it and read. Taiwan became a great superpower in semiconductors. And then China took on. The last big country that has developed this ecosystem is China. And now we are again, India is one of the few countries that is trying to leverage what I showed you earlier. We have great designers, we have a lot of good R&D institutions and colleges, and we have a large consumer base. So India is trying to create this whole system, ecosystem. Now the names that you see at the bottom here, Texas Instruments, Samsung, all of these people have large presence in India. Very large presence. And they have been leveraging the Indian talent for many years because we were very good at designing. We are now putting up, Tata has put up the first fab, or put up is in the process. Micron has put up the first assembly test. And we have now around 10 companies in this space. The opportunity that is there for us is to expand now to get into the materials, to get into the equipment manufacturing space where a lot of our talent is there. Applied materials, we have 8,500 people. So how can we support them from the local ecosystem? And then, of course, the output of this would go into companies that like Tata and Foxconn, who make the iPhones, who make the BYD material, equipment, who make the EV cars from Tata and all the companies that are in the EV market. So this whole ecosystem will take around at least 10 years to become resilient. And all of us have realized during the COVID that a $20,000 car can stay in the parking lot waiting for a $1 chip. So many developed countries where they have the talent, they are trying to get this whole ecosystem so they don't get stuck like that. India is the largest source of talent, and all of you on the line are a part of that talent ecosystem. So to make this whole ecosystem work, let's look at what type of people we need. And it is my emphasis is that this is beyond just electronics engineers. The EDA tools and chip IP process, you need software engineering, you need to understand electronics. The materials, you need chemical engineers, you need material science engineers. Wafer fab equipment, you need mechanical engineers, systems engineers, manufacturing engineers, software engineers to make the tool work, the chemical engineers to make sure that the process is working. You need manufacturing engineers. Product safety. Safety is a big thing because you're going to use hazardous chemicals. These are very high dangerous materials. So you need very high focus on reliability. You need very high focus on safety. So just see how many different types of engineers you require. The IDMs, you need electronics engineers, you need material scientists, you need chemical engineers. The fabless companies will require electronics engineers, software engineers. The foundries like TSMC or Tata that is coming up, they will require everything that I said about the wafer fab equipment. They need mechanical engineers, and so many people are required and suppliers are required to run the fab. It's an enormous project. Every fab is more than $10 billion. And to run it efficiently, to make money, you need to keep it very clean and at very high uptime. The same thing goes for, yes. Is there a question?
Questions?
Did anybody have a question?
I think no, sir. I think.
Okay. So I wanted you all to get a sense that semiconductors is more than design. And I hope this slide gives you all a good idea of how, especially from the education system, how do we make sure that our students understand that the scope is way beyond just electronics and computer science. Any questions?
Yes, sir.
Go ahead.
Sir, an engineer who is interested in working or having the knowledge of assembly, testing, and packaging, does he or she needs to learn the um, backend or the background of all the design, what the electronics engineer or software engineers do?
No. The assembly test manufacturing engineer, the assembly test person, they need to know how to run the factory. They need to understand the testing or the performance of the chip. And they need to understand the failure analysis. If there is a yield loss, that means your defects, you need to be able to do a failure analysis for which you will require some knowledge of the electronic circuit. But you don't need the knowledge of designing it. You need to know how the chip is designed to give the output that is needed. You understand the difference? One is to design the chip. The other one is the skill you need is to understand how it is working. So for assembly test and packaging, you need to understand how the chip will work, from making sure that your test results or the yields are very good, meeting the requirements of the expectations that you want from the chip, and for failures to be able to do the failure analysis. Does that help?
Yes, sir. Thank you, sir.
Welcome. Any other questions?
No, sir.
To cover all this, remember one other important thing. None of these work without proper supply chain and logistics. You have to move material and buy material, good suppliers, good quality, and you'll have to move it in a very efficient manner all over the country, all over the world. Some of these things you may even have to do international. So supply chain and logistics becomes a very critical part of this whole ecosystem. And that is where I spent a lot of my last 4 years, right? During COVID or after COVID, I spent a lot of time, and I'm still doing a lot of that work in my current role. How do we make sure that you find the right suppliers who can do, and it goes across every of the step. So I want you all to remember, to get in semiconductor industry, supply chain knowledge is also very critical. You need very good supply chain and logistics people. The logistics here is very different. Like, for example, how do we ship hazardous material becomes a very critical part. How do we make sure country of origin, because of all the geopolitical pressures going around the world? To understand what is country of origin, how do we make sure the HTS codes are correct? So there are lots and lots of things that are critical and become very complex in this industry. All right, I'm going to share a couple. If there are no other questions, I'm going to switch to a little bit about applied materials. Any questions on any of these slides that we talked about?
So the portion we are teaching in the classes are very basic, because we are teaching the full adders, half adders designs. But how they can get to know about what is customer requirement at the industry level, and that can be incorporated to the academia, so that
Yeah.
students can directly relate their study to the industry needs.
Yeah, so customer requirement for each of these steps is different, right? So what is the customer requirement of, let's take IDM? They are going to design the chip. They need to go and talk to the customers like Apple and the end consumers. Or let's take the example of Samsung. Samsung designs the chips, manufactures the chips, also makes mobile phones. So if that group of chip design does not talk to the mobile phone company, the group of that makes the mobile phones, the product will not meet requirements. So they have to talk to them. Similarly, in you all need to have a generic course at least that explains to the students that important aspect of chip design is understanding customer requirements. How do we gather customer requirements? How do we document them? How do we make sure that the product that is being designed is going to meet those requirements? So you can't create a chip design out of vacuum. You need to know what you're aiming for. And I'm not saying any of this thing is easy. I'm trying to give you all a big picture that academic curriculum aspects, there should be at least one as an ecosystem. It is not only chip design or only software. It covers so many steps. This, recently I was there in Bangalore in Ramaya Institute. There also I gave the same example. I said, somewhere the students early on in the first year should understand that the ecosystem of semiconductors is beyond computer science and electronics. And
Any other
I'm
questions?
looking at y'all to take this back to the government, to the 𝗕𝗫𝗄𝗎 or whatever, who sets all the standards for them to understand. And I know that we as Applied Materials spent enough time with 𝗕𝗫𝗄𝗎 and 𝗕𝗵𝘂𝗶𝗰 Vaishnav and others to explain this concept. They get it.
Yes, sir, because there is a very huge gap between the students, academicians, and the industry people.
Correct.
So unless and until the students get trained or the faculty get trained in this semiconductors area.
Absolutely. You said it. And y'all have to leverage companies like us to help y'all make sure that the government understands it, the education department understands this. Like I said, Ashwini Vaishnav, he gets it. If you have seen his YouTube videos, he has visited my lab. He has spent time with me to understand. And he has gone and educated other people in the ministry. He has a nice YouTube on that.
Yes, sir.
But it is in the interest of India that y'all as the academicians take this to them to understand that, make them understand that the curriculum should be a little wider, giving students more choice.
Yes, sir.
Anybody else? Any other question?
Any questions, please? No questions, sir.
Okay. All right. Applied Materials is in 5 locations in India. We are the second largest facility outside US in India, and we cover almost all aspects of the business. As like any multinational, we started doing some basic work from India, but now we design full tools from India. So it's grown in capability and by leaps and bounds. And now full products are designed out of India. Of course, we don't do manufacturing. We have labs that does a lot of advanced research work. You can see we started in 2002 and progress over a period of time to what we did in 2005. We built our own facility in IIT Bombay, and then we have built a lab here in Bangalore. And from the last 3 years, we have been interacting very, very closely with the government for both the semicons. Prime Minister Modi came to our booth, spent time with us. As I explained, Ashwini Vaishnav was in this is our lab, which was inaugurated by the Minister Ashwini Vaishnav. So a lot of interaction, a lot of close interaction with the government to develop this ecosystem. As a summary, let me just say, don't think of semiconductors only as electronics. The value chain is wide, and unless we put all these several pieces together, India cannot become a powerhouse. China has done this very well. So we have always, I remember a phrase in TI, steal shamelessly. As long as you're not from public knowledge, steal shamelessly. Don't try to copy from protected IP. But today, Google, AI will give you so much information. So we can learn from the mistakes that other countries did, so we avoid those mistakes. Just like I showed in product design, think about all the mistakes done in the design that did not work. Similarly, think of all the mistakes that other countries made, so we avoid those. Core engineering subjects like mechanical and electrical dominate that ecosystem more than software and semiconductors and electronics. To make the whole ecosystem work, the core engineering subjects are very important. Supply chain and logistics is critical for all streams. With that, that is the end of my thing. I hope this was useful. If there are
Yes,
any
sir.
last questions, I'll be happy to take them.
Any questions, please, participants?
Sir, I think AICT or any agencies should financially support the academics to purchase the tools that are required for the designs. At
There are
least,
a lot of universities that are setting up fabs. So I just met on Monday one of the 10 companies who's setting up a fab in Odisha. He's also in US coincidentally. So we had a 1 hour discussion. So in IIT Bhubaneswar, he has set up a pilot line funded by government. The fab is being funded by government. IIT Bombay has a semiconductor lab. SCL, government is putting a lot of money into refurbishing SCL semiconductor complex. So I think money is being there. If your university needs it, you all should put a proposal. And I'm sure there is funding available. Funding is not an issue as far as I know. As far as I know, today in India, funding is not the bottleneck. It used to be long ago. I know because I know how many R&D projects I do with multiple government organizations across the country. Several IITs. I have a project which I'm personally driving with IIT Madras.
Yeah. Any other questions, please?
Good.
Ian asking
So
any other?
if there is any survey and if there are any comments, do let us know. I'll be happy to come and talk on this topic to your students, to your faculty, or to the government agencies. This is a topic that Applied is very passionate about to develop the ecosystem in India. We have spent a lot of time and our own money to work with the government, and government has also been extremely responsive and receptive to our ideas.
sir, we are just waiting by what time our university or students, faculties will be involved in this process and and joining the Fab Labs, and will be easily working with proper training. So
Yeah,
we
so
are.
that great point. IIT Gandhinagar is setting up a training. They're getting tools from several companies to train. And the first fab is coming in Dholera in Gujarat, not only to support them, but support the whole country. So you all should stay connected. Most important is the awareness. I think once you all spread the awareness on this, things will start flowing. In every meeting that you all have with the government, you all should be thinking on this broad sense. Things will happen.
Yes, sir. Thank you so much, sir, for delivering such a nice presentation.
I hope it was useful. I don't
Yes,
know.
yes.
I'm
Yes,
passionate
sir.
about this topic, so I wanted to share this.
Yes, sir. It was actually a very wonderful session, sir. Even amateurs like me, we also could understand so much about semiconductor industries. So, any other questions, dear participants, please? Okay, I think there is no question. So, thank you so much, sir. Thank you, really, thank you so
Welcome.
much. So, we, Dr. Hitesh, and myself, Dr. 𝗓𝗧𝗔𝗟, we give thank you again for your valuable contribution and for your time and effort you have shared with us today. Thank you so much, sir. We are really honored to have you as our speaker. Thank you so much.
Thank you, sir,
My
very much,
pleasure
sir.
and my honor. Thank you for inviting me, and Happy New Year to everyone.
Thank you, same to you,
Happy
sir.
New Year.
All right, take care,
Thank you,
guys.
sir.
Okay.
Thank you, sir.
So, ma'am, please
Thank
announce
you,
tomorrow.
sir.
Tomorrow's session
Thank
will
you.
start from.
Okay. Okay, so here we are concluding the day 5 of FSFM 2025. So, so tomorrow is the last day of FSFM. So I request you all kindly join at 2 p.m. tomorrow. And there are 3 sessions, and I promise there are very wonderful sessions by Dr. Sumit Saha, who is from NIT Rourkela. Another is from Dr. Arghya Tarafdar, who is from IIT Kharagpur, and another is from Dr. Sushant Tripathi, who is from KIT. So please join tomorrow at 2 p.m. And thank you so much and good night.
Thank you, ma'am.
Thank you,
Thank you.
madam.
Thank you, madam.
Can leave now.
Okay, sir.
Okay, thank you, ma'am.